Hello, good morning, everyone. Today is Tuesday, August 25th, 2020. It's 10 o'clock time in Johor Bahru. So we are very fortunate today to have a distinguished guest, Professor Mark Crocker from the University of Kentucky in Lexington, Kentucky. This is the 40th Distinguished Lecture Series. And Mark and I have known each other for about over a year. So actually our collaboration started when he invited me to contribute to a book chapter on biodiesel. And so I was happy to accept that invitation. After a few months, I decided to apply for the Fulbright Scholar Fellowship, and one of the prerequisites is to get a host. And so I thought about Mark and wrote him an email asking if he could host me for the visiting Fulbright Fellowship. And when he said yes, I was so happy, and I applied for the Fulbright Fellowship and I got it. So in September last year, I spent about 3 months at University of Kentucky under the supervision of Professor Mark Crocker. So that's how we collaborate. And okay, Professor Mark Crocker is actually a very good cook. He likes rendang. Okay, he likes chicken rice, and he knows how to do it. He knows how to cook it, and he also likes tempeh. So hopefully, Mark, you can come to Malaysia so I can cook for you, because during my visit to Kentucky, I didn't know he likes rendang until the very last day when I wanted to leave. Okay, so over to you, Datuk Rafi.
Thank you, Prof. Nur Aisha, for chairing the session. Assalamualaikum. Hello, welcome everyone. Welcome to our 40th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Mark Crocker from the University of Kentucky, USA. A bit about our distinguished speaker today. Mark Crocker received BSc and Ph.D. degrees in chemistry from the University of Bristol in the United Kingdom and spent 2 years as a NATO Research Fellow at the University of Wisconsin-Madison. Thereafter, he spent 15 years working in industry, first for Shell Research in Amsterdam and then for Degussa's automotive catalyst division in Michigan, USA. In 2003, he moved to the University of Kentucky, where he is currently a professor in the Department of Chemistry and an associate director of the Center for Applied Energy Research. At UK, at the University of Kentucky, he leads a research group focusing on carbon dioxide recycling using microalgae, biofuels, and environmental catalysis. So that is a brief biography of our distinguished speaker. Here now is Professor Mark Crocker from the University of Kentucky, USA, with his talk entitled Oxidative Catalytic Depolymerization of Lignin and Lignin Model Compounds. Professor Mark Crocker, over to you.
Well, thank you so much for the kind introduction, and let me say what a pleasure it is to be talking to you today. So thank you for the invitation. And I also hope that everybody is keeping well in these rather difficult times. So today, as you heard, I'm going to be talking about the oxidative catalytic depolymerization of lignin and lignin model compounds. To give you an idea of the structure of my talk, I'll begin with a brief introduction outlining what lignin is and why we're interested in depolymerizing it and converting it into other bioproducts. I'll then talk a little bit about our approach to lignin depolymerization and some of our more recent results. And after that, I'll move on and discuss the results of a comparative study of secondary oxidative lignin depolymerization methods. And then I'll finish, hopefully, with some conclusions. So what is lignin? Well, as you may be aware, plants are composed of 3 main biopolymers. That's to say cellulose, hemicellulose, and lignin. Lignin itself is an amorphous and irregular polymer which is produced in planta via the phenylpropanoid pathway. And this involves a radical-based polymerization of three monomers, or so-called monolignals, namely synapyl alcohol, coniferyl alcohol, and coumaryl alcohol. And lignin is important because it occupies a number of it performs a number of specific functions in plants. Specifically, in the cell wall, it acts as a sort of structural glue and protects plants from chemical and bacterial attack. Additionally, it aids in the transport of water. So here you see the distribution of these three main biopolymer constituents in some common types of lignocellulosic biomass. And you can see that cellulose is the dominant biopolymer present, followed by lignin and hemicellulose in roughly equal amounts. Now in grasses, lignin typically occurs at no more than about 28%. In trees, of course, such as softwoods and hardwoods, it's higher. And indeed, in softwoods, lignin can comprise up to about 30 to 35% of the weight of the biomass. So why are we interested in depolymerizing lignin? Well, there are really two main reasons for this. First of all, if we want to produce aromatic chemicals and fuels in a sustainable manner, then really lignin is the only available starting material in nature. And you can see that it has a highly aromatic character, giving rise to the idea that we should be able to produce a wide array of aromatic compounds from it, if we can find suitable methods for its depolymerization. Secondly, lignin is produced in large amounts, essentially as a waste product of the pulp and paper industry. Indeed, something like 50 million tons are produced every year. Some of this is burnt as a low-grade fuel. However, some of it has to be disposed of in landfills because there's no real use for it. Moreover, if cellulosic ethanol refineries start to ramp up, then of course lignin will also be produced as a waste product there. Moreover, certain recent techno-economic analyses have shown that the economics of cellulosic ethanol production are highly dependent on the value that one can obtain for the lignin co-product. In other words, if we can actually convert the lignin co-product into more valuable materials, then this can greatly improve the overall economics of cellulosic ethanol production. Now, as I mentioned, lignin has an amorphous, irregular structure. However, there are certain types of linkages that can be identified in the lignin macromolecule. And among these, the beta-O4 interunit linkage is the most prevalent. Indeed, it accounts for between 50 and 60% of all the linkages in lignin typically. And by interunit linkage, what I mean really is the linkage between the aromatic moieties in the lignin macromolecule. Now, of course, there are also other linkages present. Some examples of these are I'm trying to use a pointer here, and unfortunately, it's not working now. But if you look at the slide, you can see some other examples, the 5-5 linkage, for example, the beta-beta linkage, the 4-O-5 linkage, etc. But because the beta-O4 linkage is the most prevalent, this is the linkage that most researchers target when trying to devise methods of depolymerizing lignin. Now, of course, if we are going to depolymerize lignin, there are going to be problems. And first among these is the fact that lignin is extremely recalcitrant. And by that, I mean it's not particularly reactive. Indeed, lignin has evolved over millions of years so as to guard plants from chemical and biological attack. Additionally, lignin is not particularly soluble. Indeed, it's only sparingly soluble in certain polar organic solvents such as DMSO and dimethylformamide. And thirdly, its analysis is very challenging. Consequently, if we're going to develop chemistry for the depolymerization of lignin, then we have to rely on model compounds, so simpler systems that we can easily characterize. Having developed the necessary chemistry, we can then try and apply it to lignin itself. And indeed, if you look in the literature, a number of processes have been developed for the purpose of depolymerizing lignin. Unfortunately, most of these involve the use of high temperatures and/or high pressures of hydrogen. So one can think, for example, of hydrotreatment, pyrolysis, which obviously involves the use of very high temperatures, solvolysis in certain organic solvents, typically again under high pressures and relatively high temperatures. And the problem with these methods is that they don't tend to be very selective. Certainly pyrolysis isn't. So for these reasons, we decided to try and adopt an alternative approach, namely making use of selective oxidation, because it's known in the organic chemistry literature that oxidation reactions typically proceed under relatively mild conditions. So say below 150 degrees C, and typically under fairly low pressures of either oxygen or in the presence of other oxygen donating reagents such as hydrogen peroxide or alkyl hydroperoxides. And moreover, these oxidation reactions are very often highly selective. So the potential advantages of the selective oxidation approach for lignin depolymerization can be summarized as the use of mild conditions, the use of inexpensive reagents, certainly if oxygen is being used as the oxidant, and the fact that in principle, we can obtain highly functionalized and therefore valuable aromatic compounds, such as vanillin, syringaldehyde, and syringic acid. And as you can see, these are all rather valuable compounds. Now, of course, there are potential disadvantages, namely the fact that we're probably going to be using lignin in an isolated form, rather than in the native form as it occurs in the biomass. And unfortunately, when one isolates lignin from biomass, this often increases the recalcitrance of the lignin. And this is due typically to the occurrence of carbon-carbon bond forming reactions during the extraction process. One can think of this essentially as a cross-linking of the lignin polymer. On this slide, I'm just making a comparison between the two main approaches for catalytic depolymerization of lignin. So on the one hand, we have reductive methods involving the use of typically hydrogen and either hydrogenation or hydrotreating catalysts. Now, these can produce monomers in good yield. Unfortunately, the process tends to be energy consuming. And because we're introducing a hydrogenation function into the process, we tend to eliminate oxygen in the form of valuable functional groups, with the consequence that our products tend to have low functionality. Typically, they're going to be things like phenolic compounds, which are usually about 100 times less valuable than these more highly functionalized compounds, such as vanillin and vanillic acid. So for that reason, the oxidative approach really strikes us as being potentially more interesting and certainly more economically feasible in the long run. Well, one of the early breakthroughs in this field occurred with the report from Shannon Stahl and his group in around about 2013, that if you take this model compound, so this is a model for the lignin beta-O4 linkage, if you treat it with certain tempo derivatives in the presence of acid and 1 atmosphere of oxygen, then you can oxidize the benzylic alcohol group here. So this would be the alpha position, and you can form the corresponding ketone in good yield. Now, why is this significant, you may ask? Well, if you look at the bond strengths in the oxidized form of the linkage, it turns out that the carbon-oxygen bond here is weaker, and significantly weaker indeed, than the carbon-oxygen bond in the unoxidized form of the beta-O4 linkage. So the comparison here is between about 161 kilojoules per mole and about 248 kilojoules per mole. So this gives rise to the idea that if you can actually oxidize the beta-O4 linkage, then you should be able to cleave the carbon-oxygen bond present in a second step. And indeed, Stahl was able to illustrate this. Specifically, he took the oxidized form of the beta-O4 linkage, and he treated it under Dakin conditions. So this involved reacting it with hydrogen peroxide in the presence of aqueous base, with the result that the beta-O4 linkage was cleaved with the formation of a carboxylic acid in good yield and also a phenolic compound. So this looks quite promising. Okay. Let me just see if I can go back. So we decided to see if we could take this approach a little bit further. Now, one disadvantage of using, say, TEMPO as an oxidation catalyst is the fact that it's a homogeneous catalyst. And of course, for industrial applications, one would ideally like to use a heterogeneous catalyst. Now, we knew from the literature that gold nanoparticles are quite active in oxidation reactions. But of course, we needed a base to be present because the literature tells us that for gold to be really active for the oxidation of alcohols, you have to have a dissolved base present, such as sodium hydroxide. So we decided to deposit our gold nanoparticles on a basic support material, specifically a lithium aluminum layered double hydroxide. So the idea was the same essentially as that of Stahl, namely to take the beta-O4 linkage and to oxidize the benzylic alcohol group present to give a ketone functionality. And then we decided that we would try and oxidatively cleave this ketone species in some kind of second step, which had yet to be decided. So at this point, let me say a little bit about layered double hydroxides. As their name implies, these are simply mixed metal hydroxides which adopt a layered structure. The general structure corresponds to that of the mineral brucite. And what's particularly interesting about layered double hydroxides, or LDHs for short, is that one can accommodate a range of divalent and trivalent metal ions in the LDH structure, and in the case of lithium, a monovalent ion. Moreover, these materials are very simple to prepare, typically by means of co-precipitation methods. They're inexpensive, and they should be extremely stable under typical oxidizing conditions. So we deposited our gold nanoparticles on a lithium aluminum layered double hydroxide. And for comparison, we also looked at the use of several other basic layered double hydroxide materials as supports, specifically a magnesium aluminum LDH and also a nickel aluminum LDH. And it was known from the literature that gold supported on these two LDHs here were active to some degree in the oxidation of alcohols. So the test reaction we performed was a very simple one, namely the oxidation of 1-phenylethanol to acetophenone. So we used a small amount of catalyst at 80 degrees C, and we found that we could actually form the acetophenone product over our gold on lithium aluminum LDH after 20 minutes. So 100% conversion after 20 minutes. And as you can see, the lithium aluminum LDH turns out to give a more active catalyst than the other two LDHs that we tested. So we then asked ourselves, well, why is the gold on lithium aluminum LDH so much more active than these other catalysts? And there are really two reasons for this. First of all, if we look at transmission electron micrographs of a catalyst, we see that we have very small gold particles. Indeed, from this histogram, you can see that most of the particles fall within the size range of about 2 to 4 nanometers. And of course, this is important for maximizing the surface area of the exposed gold. Secondly, when we perform X-ray photoelectron spectroscopy on these materials, we find that the gold, specifically the gold 4F level, has shifted relative to bulk gold. So if you look at the positions of the 4F5/2 and 4F7/2 peaks, these are shifted significantly from their positions in bulk gold. And this is indicative of a transfer of electron density from the basic support material to the gold nanoparticles. Moreover, the shift in binding energy to lower energy is greatest for the lithium aluminum LDH, followed by the nickel aluminum LDH, followed by the magnesium aluminum LDH. And indeed, this follows the order of catalytic activity of these catalysts for alcohol oxidation reactions. So clearly, the transfer of electron density from the support to the gold nanoparticles is critical for an active catalyst. Well, we went on to look at a number of other benzylic alcohols, as shown here. Again, using our gold and lithium aluminum LDH catalyst, using 1 atmosphere of oxygen. That's to say we simply bubble oxygen into the reaction mixture. And you can see that in all cases, we were getting good conversions. And the yields are very close to the conversions, as you can see, which means that the selectivity is almost 100% in pretty much all cases. And I'd like to draw your attention to entry number 7 here. In this case, we used an alcohol bearing a cyclopropyl group. And you can see that we obtained the corresponding ketone in very good yield. Now, the fact that we don't see any products derived from ring opening of the cyclopropyl group tells us that free radicals are not involved in this oxidation process. Because if they were, we would expect to see the formation of ring open products. So this is telling us that the oxidation reaction proceeds via a 2-electron oxidation mechanism. So from there, we went on to look at the performance of our catalyst with beta-O4 model compounds. So starting with this particular compound here, you can see we have, again, an alcohol in the alpha position, and we also have a gamma alcohol group here. And when we treat it with our catalyst at 120 degrees C, we form the expected oxidation product here. However, this reacts further. Now, there are 2 possible reaction pathways that can be followed. The minor one involves the dehydration of this gamma alcohol group to form an enol ether here. Now, this in itself is not a bad thing because, of course, enol ethers can be readily cleaved by the addition of a catalytic amount of acid. So if we do form the enol ether, that's not really a problem. We should be able to cleave it in a second hydrolysis step. However, the main reaction pathway involves a retroaldol reaction here at the gamma alcohol group with the elimination of formaldehyde and the formation of this ketone species here. And under our reaction conditions, this reacts further. The carbon-oxygen bond here is cleaved with the elimination of this methylene group here as carbon dioxide, and we form this aromatic acid and also this phenolic compound. However, the story doesn't quite stop there because, of course, we have an acid here and an alcohol, and we have a catalyst which is basic in nature, and of course, bases will catalyze esterification reactions, and so we actually tend to form this ester here. Again, this isn't necessarily a problem because, as we all know from high school chemistry, esters can be readily cleaved by the addition of a catalytic amount of acid. As regards the proposed oxidation mechanism, we don't have too much information, but we believe the mechanism follows roughly this pathway. Namely, we think that the oxygen is absorbed onto the gold. Given that the gold is negatively charged to some degree, we believe that there is a transfer of electron density from gold to the oxygen, presumably to the oxygen's pi star orbital. At the same time, the alcohol is deprotonated by the basic support, and this results in the formation of an alkoxide group. Now, transfer of hydrogen from this alkoxide to the partially negatively charged oxygen here on the gold would result in the elimination of the ketone and the formation of this hydroperoxy group on the gold. And then a couple of steps will then take us back to our starting species here. And again, I should emphasize that this is a 2-electron oxidation mechanism, and so we don't have to invoke the presence of free radicals. So now the big question is, what happens with lignin itself? So to look at this, we used two different types of lignin, namely a craft lignin, which is obtained from a commercial source, and also a lignin extracted from maple using gamma-valerolactone. Now, gamma-valerolactone is a solvent which has been championed by Jim Domesic at the University of Wisconsin. It's actually derived from biomass, and it's an extremely good solvent. Indeed, lignin is fairly soluble in it. So we took these lignins, we dissolved them in dimethylformamide as the solvent. We added our catalyst, and again, we're using 1 atmosphere of oxygen, so we're just bubbling oxygen into the reaction mixture and a temperature of 120 degrees C. After that, we performed a second step, namely we took our oxidized lignin samples, we dissolved them in a little bit of dilute base, and then we stirred for about 30 minutes, after which we added a little bit of acid until the pH was slightly acidic. And we did this because, as you may recall, we believe we're forming an ester from the cleaved beta-O4 linkage, and possibly also forming an enol ether. And of course, both of these species will be readily cleaved under these hydrolysis conditions. And then finally, we extracted the reaction products into ethyl acetate. So now let's look at our lignin before and after oxidation. And to do this, we use HSQC NMR, so 2D NMR spectroscopy. So on the left-hand side here, you can see the NMR spectrum of our craft lignin starting material and also our GVL lignin. And here you can see the spectra of the same lignins after oxidation. Now, in the spectra of the starting lignins, I'd like to draw your attention to these cross peaks shown in turquoise. These correspond to the alpha, beta, and gamma CH groups in our beta-O4 linkage here. Or in the case of the gamma, it's actually a CH2 group. And what you can see is that after oxidation, these signals have disappeared. In other words, the beta-O4 linkage is no longer present. Additionally, in the spectrum of our starting GVL lignin, you can see a signal here, which we attribute to the beta carbon of this oxidized form of the beta-O4 linkage. However, in both of our spectra here of the oxidized lignins, you can see that this signal is absent. So clearly, the simple oxidized form of the beta-O4 linkage is no longer present either. And it's also interesting to note that we observe the disappearance of signals corresponding to the beta-5 linkage, which are shown in green here. And we also observe, largely speaking, the disappearance of the signals corresponding to the beta-beta linkage. Now, in the case of these two linkages, we're not sure if we're actually breaking them. What we could be doing is simply dehydrogenative atomization of the furan rings here. That would also cause these signals to disappear. However, in the case of the beta-O4 linkage, it does seem to be the case that we are destroying the original linkage. If we look at the aromatic region, it's pretty complex. I won't go through it in detail. Suffice to say that one of the main observations we make is that we observe the disappearance of these guaiacyl groups, and that's consistent with the fact that we are cleaving these beta-O4 linkages. So after that, we performed the hydrolysis step on our oxidized lignin, and we extracted the resulting products into ethyl acetate, and we analyzed them using GCMS. And what you see is that in the case of the craft lignin, before hydrolysis, we have a 10% yield of material which is ethyl acetate soluble, whereas after the hydrolysis, we have a 20% yield of soluble material. And in the case of the GVL lignin, we have 20% before hydrolysis and 56% after hydrolysis. Now, if you look at the shaded bars here, This gives you the yield of monomers. So in the case of the kraft lignin, after hydrolysis, we have about a 9 to 10% yield of monomers, whereas in the case of the GVL lignin, we have a 40% yield of monomers, which is actually quite a bit higher than we had dared hoped for. So here you see the breakdown of the monomers. In the case of the kraft lignin, we have only G-related products, specifically vanillin and vanillic acid. And that's because this kraft lignin is derived from pine, and pine doesn't contain any S units, any S monomers in its structure. It only contains G monomers. Now, in the case of the GVL lignin, because it's derived from maple, we have products derived from both G and S monomers. Indeed, we see the formation of vanillin and vanillic acid, syringaldehyde, and syringic acid. And again, all of these monomers are valuable compounds. We also analyzed the ethyl acetate soluble material by means of gel permeation chromatography. In the case of the kraft lignin, here you're looking at the starting kraft lignin. This is actually dissolved in DMSO, and you can see we have a molecular weight of, or an average molecular weight, I should say, of a little bit below 10,000. In the case of our kraft lignin post-hydrolysis, you can see that we still have some fairly heavy material present. So clearly this is lignin which hasn't completely depolymerized. However, we also have a strong peak here corresponding to monomers and probably also some dimeric compounds. In the case of the GVL lignin, before oxidation, again, we have a fairly high molecular weight. After oxidation and hydrolysis, the molecular weight has decreased here slightly, but again, we have a significant amount of material corresponding to mainly monomers. So again, this confirms that we have been able to depolymerize our lignin to a significant degree. Well, that's all well and good, but we then wanted to compare our depolymerization results with those reported in the literature. And this turns out to be an extremely difficult problem. The reason being that there is no such thing as a standard lignin. Every research group in the literature uses their own particular lignin, and because lignins differ so much in their properties, you can't really compare the results for one lignin with those for another lignin. So how can we make an accurate comparison? So the way we decided to do this was to repeat our experiments using a two-step oxidation approach. We did this because most depolymerization methods in the literature do use such a two-step approach. So you recall in Stahl's work that what they tried to do was take the beta-O4 linkage, oxidize it in the first step to the corresponding ketone, and then subsequently cleave the oxidized form of the linkage using some secondary method, such as Dakin oxidation. So what we did was we took a large batch of lignin, we subjected it to a standard oxidation procedure, and then we took that lignin and we subjected it to a number of literature secondary oxidation methods. So for the initial oxidation step, we used a method published by Lansfield et al. And this involves the oxidation of, again, our kraft lignin and also our gamma-valero lactone extracted lignin. In this case with DDQ, so another organic catalyst, in the presence of tertiary butyl nitrite and oxygen, again, 1 atmosphere of oxygen. So this gave us oxidized kraft lignin and GVL lignin. And then we subjected these materials to a variety of literature protocols. So for example, a zinc-mediated lignin depolymerization reported by Westwood and co-workers, formic acid induced lignin depolymerization as reported by Shannon Stahl, a Bayer-Villiger oxidation approach, which we have reported in collaboration with my colleague, Professor Mark Meyer, Another approach involves oxidative lignin depolymerization using copper ions in the presence of phenanthroline. This has been reported by Wang's group in China. We also have Dakin oxidation, which I showed you previously, reported by Shen and Stahl. And then for comparison, we used our gold on lithium aluminum LDH. And we also wondered what would happen if we didn't have the gold present. So we also tried just using the lithium aluminum LDH material itself. So here you see the results. On the left-hand side, I'm reporting the results for the Kraft lignin, and on the right-hand side, the results for the GVL lignin. And so the bars here correspond to the amount of ethyl acetate soluble material, and the solid part of the bar refers to the yield of monomers, again in weight %. So you can see that in the case of the Kraft lignin, our essentially one-step gold on lithium aluminum LDH method, as I told you earlier, gives about a 9 to 10% yield of monomers. And the formic acid hydrolysis method of Shannon Stahl gives a similar result. The gold on lithium aluminum LDH catalyst, if we use that on the oxidized lignin, we get a similar yield of monomers as you would expect. The lithium aluminum LDH without any gold gives a lower yield of monomers. That's not too surprising. We really do need the gold there. And these other literature methods really aren't very effective at all. If we look at the GVL lignin, then of course with our gold catalyst, we get a 40% yield of monomers. If we take the oxidized lignin and then treat it with our gold catalyst, the yield of monomers actually goes down a little bit. This was a bit surprising to us. We actually thought that the yield might go up even a little. But we think the reason that the yield is lower is because the oxidized form of the lignin actually isn't as soluble as the initial lignin, i.e. the unoxidized lignin. So because the oxidized lignin isn't as soluble, it doesn't react quite as much as the unoxidized form. So the next best method is the formic acid hydrolysis again, but now we're only getting 11% yield of monomers. Again, the lithium aluminum LDH without the gold doesn't give very good yields. So again, we do need the gold. And these other literature methods are basically pretty ineffective. So I think this is a good indication that our gold on lithium aluminum LDH catalyst, it is extremely effective. And certainly it compares very favorably with the other methods that have been reported in the literature. Now, of course, the one disadvantage of our method, although it is a heterogeneous catalyst, is the fact that it does contain gold, namely 1 weight % gold. And of course, gold is not the cheapest of metals. So obviously, we would like to be able to decrease the amount of gold in our catalyst, either just by decreasing the loading, or perhaps by alloying the gold with another metal, hopefully a less expensive metal, which also shows activity as an oxidation catalyst. And so this work is currently ongoing in my group. So I think I'm running out of time, so I will finish now with some conclusions. Hopefully I've convinced you that our gold on LDH catalyst shows excellent activity in the oxidative cleavage of beta-O4 model dimers. And we find that an ester moiety is formed. That's the ultimate product from the oxidation of the beta-O4 linkage dimer. However, we can cleave that ester using a simple hydrolysis step after the oxidation. And indeed, according to HSQC NMR data, we observed the disappearance of both unoxidized and oxidized beta-O4 linkages in lignin. So again, we think this is consistent with the formation of an ester linkage, which of course isn't going to be NMR active as far as 2D NMR is concerned. We also find that our gold on lithium aluminum LDH catalyst gives higher monomer yields than other oxidative approaches reported to date. And on this basis, we think our catalyst shows a good deal of promise for further development, although clearly we do need to try and devise a less expensive catalyst, let me put it that way. So with that, it just remains for me to thank the people involved in this work, particularly Dr. Vanessa Song. Vanessa was a graduate student who was responsible for essentially all of this work. She's now an assistant professor at Centre College in Kentucky. Dr. Justin Mobley, who at the time was a postdoc in Dr. John Rolfe's group in Madison, he obtained the HSQC NMR spectra that I showed you. Mark Isaacs, Karen Wilson, and Adam Lee were kind enough to teach Vanessa the basics of XPS spectroscopy. And James Domestic at UW-Madison and his graduate student Ali Mosingamwala were kind enough to provide us with GVL lignin. And of course, I have to thank the funding agencies involved, namely the National Science Foundation and the British Council. And of course, thank you for your attention.
Okay, thank you, Mark. So it was very interesting. A lot of chemistry involved there, and we have to digest a lot of things this morning.
Hopefully it won't give you indigestion.
Huh?
Hopefully it won't give you indigestion.
Yeah, it's okay. The questions that I have is about the analysis. Okay, for example, when you did the molecular weight, you did that. You wanted to see, okay, what are the molecular weights? How do you do it? Which type of equipment do you use to measure
using an HPLC setup using a gel permeation column. So a feature of the column is that the larger compounds tend to get trapped in the pores of the column, and so they take. Let me get this right. So they don't get trapped to the same degree, so they elute first. The monomers tend to get trapped, and so they elute later. And so you get a separation based essentially on the size of the molecule, but that corresponds roughly to the molecular weight.
Okay. Yeah, the other thing is about the NMR. Characterizing. It's a special type of NMR. Is it? You mentioned what NMR SH, what the analysis?
HSQC. Heterospin coherence NMR. Really, that's just a fancy term for 2D NMR. So it's proton carbon 2D NMR.
So what is the alternative? Like if we don't have that available for this NMR, so what are the alternatives that we can use for analytical method or analyzing that?
In the case of lignin, you really do need to use 2D NMR. It's kind of the gold standard for lignin characterization. Pretty much everybody uses it. However, you will find that there are certain groups around the world who will actually do it for you if you ask nicely and you collaborate with them. So, for example, John Rolfe's group in Madison, they did a lot of our 2D NMR initially. Nowadays, we tend to do it ourselves here in Kentucky. But I would suggest you collaborate with a group that does a lot of 2D NMR, and they can certainly help you. Without 2D NMR, it's extremely difficult to characterize lignin, unfortunately.
Okay. Yeah, well, we have a question here from Muhammad Al-Mola. Can you read the question, Mark?
What kinds of oxidation materials can we use in food to prevent it from oxidation in a safe way? So I guess you're probably talking about free radical inhibitors here, because when food oxidizes, it tends to be a result often of free radical chemistry. So, for example, things like fats spoil due to the formation of free radical groups on the backbone of the fatty molecules. So there are a number of synthetic compounds which can be used. The most widely used one that I'm aware of actually is vitamin E. which is a natural antioxidant. And I know that that is used in some foodstuffs to prevent them from spoiling.
Okay. Yeah, Mark, the other thing that I'd like to ask is about the reaction itself. So you are using the lignin in solid form and then oxidize it with the oxygen. Is that right?
So we're trying to dissolve as much of the lignin as we can. So we're using dimethylformamide as a solvent. It's not the nicest solvent in the world, but it is the best one for lignin that we found. And importantly, under these conditions, it's stable with respect to oxidation, because clearly we don't want our catalyst to oxidize our solvent. That wouldn't be a very good thing. So whether all of the lignin dissolves initially, it's probably not all dissolved, but as the reaction proceeds, most of the lignin does dissolve.
Okay, so then your products, you will then take it not online, but it's batch. It's in a batch form.
Yeah, so far we've been doing this in batch fashion. One of the goals is actually to convert this to a continuous process. And that would involve using essentially a CSTR, so a continuously stirred tank reactor, with the catalyst contained in a basket in the reactor. We think that is probably the best way to convert this into a continuous process. And that could work. And indeed, people have done a reductive lignin depolymerization. So if you like, sort of under hydrocracking type, mild hydrocracking type conditions. And that's what they've done. They've used essentially a CSTR with the catalyst contained in a basket.
Yeah, okay. Are there any other questions online from the audience? Going once, twice? All right then, Mark. I think we should stop. It was really enjoyable. A lot of information that you gave within that short time. So thank you so much. So hope to see you here again.
And I'm looking forward to getting a cooking lesson from you.
And visit us here, Mark.
Absolutely.
Please do come.
Yes, I would love to do that.
Yes, and send our regards to your lovely wife. And take care.
Okay, thank you very much.
Okay.
Do the best for your family.
Yes.
And take care. Bye for now.
Bye-bye.